welcome to this seminar series of EuPRAXIA. Our speaker today is Dr. Riccardo Pompili. He is a researcher at LNF-INFN, the Laboratory Nazionale di Frascati. He is a scientific coordinator of Spark Lab and head of the plasma working area of EuPRAXIA at Spark Lab. Riccardo got his PhD in physics in 2013 at the University of Rome, Tor Vergata, with a thesis on the development of an electro-optical sampling diagnostics for beam-driven plasma wakefield accelerators, for which he was awarded the Young Scientist Prize by the Italian Synchrotron Light Society. Currently, he is the scientific coordinator of the Spark Lab accelerator activities and leader of plasma working area for the EuPRAXIA at Spark Lab project. During his scientific career, he's got a broad experience in accelerators and plasma physics. He has published several pioneering works, and in 2025, he received the Higel-Kim Prize for his early career achievements at the IPAC conference in Taipei. So before we start, just a reminder that you can ask questions. You see at the bottom of your screen a Q&A, so you can put your questions there, and also at the end of the seminar, you can ask your questions directly. So Riccardo, the floor is yours.
Thanks, Riccardo, for the kind introduction, and welcome to all the people following this seminar. As we'll see, I'm going to show you some way to manipulate beams before and after actually a plasma stage that we will use for accelerator or in a different way. And we can start. Okay, let's start from the beginning. Why we use particle accelerators? Because we need probes with which investigate matter at the subatomic level. And in that sense, we use the well-known de Broglie hypothesis, where the resolution actually of our microscope, that is the accelerator, is actually directly proportional to the energy of the particle. So if we increase the particle energy, we, let's say, enhance the resolution of the microscope. And that's why we need, with time, larger and larger energies to reduce the resolution to the wavelength of the microscope. And this requires actually the construction of huge machines. If we think, for instance, to the Large Hadron Collider at CERN, which is a 27-kilometer length ring. And the reason for this is because with accelerators, at least conventional accelerators, we are limited in the maximum accelerating gradient we can achieve. So the problem is that with the standard way to accelerate, that is the radio frequency technology, we have metallic cavities, and we put radio frequency energy inside these cavities to have a wave that propagates and accelerates the beam. But as you should know very well, if you put too much energy, there is the electrical breakdown that come up, and so there are sparks in the cavity, and these sparks actually can produce damages, as you can see in these pictures. And if you continue with such operation, actually the structure is damaged and you have to replace. So we can say that we are limited to fields that can reach 100 or something more with, for instance, 6-band RF technology. But we cannot go above this point. And for this, we have to add structure to reach much larger energies. That's why Luigi Mendoza actually thought to the idea of plasma or plasma-based accelerator, because plasma is an ionized medium. So we have the ions divided by electrons. So we can say is already damaged, and we cannot damage anymore this new medium. That's why plasma can, in principle, reach much larger fields that are order of magnitudes larger than what we got with the radio frequency technology. And this can be computed by simply using the Gauss theorem So if you think to a sphere with positive charge inside, and you calculate the electric field of such sphere, depending on the ion density, you get some field. If you put the numbers I used in red, so for instance, 10 to the 16 ions per cubic centimeter, you can reach tens of gigavolt per meter field. So you see, we are order of magnitude higher than radio frequency technology. That's why plasma is very appealing as an accelerator medium. However, the working principle of a plasma-based accelerator is different from a radio frequency one. In a radio frequency, you put the wave and then your beam that is accelerated. In a plasma, you need actually two guys. The first one is the, let's say, who transfer the energy to the plasma, that we call the driver, and it can be a particle beam or a laser pulse. And then we have the witness, so the beam that we actually want increase its energy, that follows the driver. We can say the typical distances of these two beams are of the order of hundreds of microns, depending on the plasma density. So you inject the driver, and the driver, what it does is remove the plasma electrons. And so we have only this positive region, that is the sphere, let's say, we saw before. And the field in the sphere actually can reach this gigavolt per meter. Then there are several ways to, let's say, produce the witness. You can external inject from your LINAC, or you can create by the plasma itself. So if the field is large enough, you can have a kind of self-injection. So the electrons coming from the plasma are also accelerated and actually make the witness beam. And actually, this is the point. So we are reducing a lot the size of the accelerator because we have large fields. But now our accelerator structure is tiny. So we have, let's say, a plasma cavity, if we can call it this way, that is 300 micron in length and around 50 micron in size. This, of course, all these numbers depend on the driver parameter and the plasma parameter. So let's assume as an order of magnitude. So the accelerator structure is very small. And this actually is good because, of course, the accelerator is compact, but can be also a problem because we have to inject the witness beam really in a precise way. Because you can see from the left plot that electrons in the witness placed at different phases actually feel different field, and so they get different energies at the end. So you have an energy spread that can be large. And also, if the beam is not well focused at the entrance of the plasma, the emittance is not preserved and can be very large too. So the real problem of a plasma accelerator is to try to do our best to achieve very good quality for the accelerated beam. And it is not trivial. So let's start with the beam manipulation. That is actually the topic of the talk. So I show you that we need actually two beams to be injected in the plasma. Now I'm talking, my talk will be mainly on beam-driven plasma accelerator, so where the driver is a particle beam. So in this case, with this scheme, we need at least two bunches produced by a standard LINAC and then injected into the plasma. So what we do here at Spark facility, we produce such bunches directly on the cathode. So we send some few laser pulses on the photocathode, and they emit few electron beams to be accelerated by the LINAC. And this can be done, of course, in a different way to produce more pulses. We reached up to 5 pulses. So we can say, for instance, 4 drivers and 1 witness, depending on the scope of the entire experiment. But in principle, we have to produce such beams before the plasma. So we have to manipulate the beam from beginning. And here actually is reported a way we do it. So we split the laser before reaching the cathode, and we have delay lines, so we can change the delay of these laser pulses before reaching the cathode. And so we tune the distance of the beam with the laser directly. That is a way to produce such multi-bunch schemes. Then we use a plasma, before the plasma, we use the velocity bunching. So the beams are produced, we have the right number of beams, but now we have to make them short because the plasma wants short and very dense beam. And so we use this velocity bunching technique. So we use the first accelerating structure to longitudinally compress the beam and reach a duration that can be of the order of few femtoseconds in principle. And this increases a lot the current of the beam because the charge is, let's say, fixed from the cathode, and then you are decreasing the duration of your beam. So the current can reach also several kiloamp. And this is a plot that shows you some typical longitudinal phase space for 2 bunches or for 3, 4, and 5 bunches. Because in plasma, we can also do so-called resonance schemes. So we inject not one, but several drivers to excite larger and larger waves. And this is all the way we use to manipulate such beams. In other facilities, they use another technique to produce a multi-bunch. For instance, at DESI, but also at SLAC, they use a dispersive section and put a collimator, let's say, to cut the beam and divide into sub-beams. So in this way, we start from the cathode with one long beam, then the beam is deflected in the dispersive section. So we have energy spread that becomes the X size of the beam, and then here you cut, and then recombine to have a 2 beam before the plasma. So depending on the facility where you go, actually you can find different schemes to produce multi-beams, multi-bunch beams. Then we have to deal with okay, we produced the beams. Now we have to properly focus at the entrance of the plasma. We saw that the plasma accelerating structure can be few tenths of micron in size. So we have to focus the beam very well to reach such size. And there is a well-known matching criteria to follow because we have to inject the beam with the right spot size, knowing the emittance. And at the end, you have to avoid the emittance spoiling if the bunch is not properly matched. So depending on the spot size you have at the entrance of the plasma, this also sets the final emittance you get after the plasma acceleration. So this is a very important step. And a typical scheme to focus the beam is this one. You can see from the right, actually, there is a triplet of magnets, in this case quadrupods, and that focus the beam at the entrance of the plasma module. And then you need another triplet to extract the beam, because now the accelerator witness has a large divergence. So you have to remove this divergence and make the beam collimated enough to be used downstream. So this is a standard way to focus and extract a beam in a plasma accelerator. And we did here in Frascati one of the first measurements of the plasma, of the emittance of a plasma accelerated beam. And we found that, of course, if the beam was not properly matched, then there is an increase of the emittance. And so you can actually exit from the plasma with an emittance that is larger than the one at the entrance. So the point is to, if you don't do a proper matching, the emittance will increase for sure. Now I'm moving to what we will do actually here in Frascati in view of EuPRAXIA. We have this project that is a EuPRAXIA at Spark Lab that will develop a new facility where there will be a beam-driven site of plasma accelerator able to let's say, seed 2 FEL beam lines with a 1 GeV beam as a starting point. So this is the let's say, well-known beam-driven pillar of the EuPRAXIA. Then there will be the laser-driven pillar in LI, but this is a different story. And of course, the reason I told you before is that because with plasma we can, especially for FEL, we can decrease a lot the size of the accelerator, and so we have much more room to host, for instance, FEL ondulators. That's why it's interesting to apply a plasma accelerator to an FEL too. And a few years ago, there were, let's say, kind of dream year for FEL driven by plasma accelerated beams. Here I report the most important ones. There are 4 works, and 2 of them actually come from Frascati, where we actually demonstrated for the first time the FEL lasing from a beam-driven plasma, both in SASI and in seeded scheme. Then there was another paper, the first one from a Chinese group that was a laser-driven one, and another paper published by a collaboration, another European collaboration that was published on Nature Photonics about another laser-driven scheme with a seed laser. Regarding EuPRAXIA Spark Lab, here is a view of how the bunker will look. So we will have all this facility in 160 meter length and 45 meter in size. And actually, this will be developed on one of the sides of the Spark Lab facility, where we did a lot of experiments so far. This is a picture, let's say, of how the building should like, and all the investment that actually has been put to construct this building, and of course all the equipment, the LINAC, the plasma, and the ondulators. And the important point is that it's very challenging task to drive an FEL with a plasma beam, because we have to fulfill several conditions. I told you that beam quality is something crucial for plasma, and so we have to take care a lot of the energy spread and the emittance of the beam, because this actually will set what we will get from the FEL. So if the spread is too large and the emittance also is too large, there is no exponential gain in the FEL, so we cannot get any radiation at the end. So that's why we have to keep them very low and preserve as they were before the plasma. And the electron parameters coming from this EuPRAXIA Spark Lab are reported in this table. So actually we foresee 2 schemes. One that is without the plasma, just the X-band LINAC, and another one where we use the plasma to boost the energy of the witness. In this case, we will accelerate an eyewitness that has a charge of 30 or 50 picocoulomb with few kiloamps peak current, and with a bunch duration that is of the order of few microns, from 3 to 6 micron, with an emittance, a normalized emittance of the order of 1. Here is the scheme of the accelerating sections. So, of course, we have the gun that generates the electrons. We have a first S-band injector, and then 2 X-band LINAC to reach half GeV energy. And then the plasma that will do the last half GeV. So at the end, we will have the 1 GeV beam ready for the FEL. The injector actually will be a copy of the Spark Lab 1. This picture actually is real, so you'll see how the Spark LINAC looks like now. And on the right, you have also different plots showing numerical simulation of the beam dynamics from the generation up to the acceleration in such a LINAC. In this case, we were using 2 beams, 1 driver and 1 witness, that have been manipulated for the plasma accelerator. Then there is the X-band LINAC, and actually the EuPRAXIA Spark Lab will be the first ever built X-band based LINAC. So we had to do a lot of R&D on the X-band technology too. This was also triggered by a strong collaboration with CERN. And here you can see we have a dedicated test facility here in Frascati, where we test the EuPRAXIA X-band cavities that then will be installed in the facility. At the end, we will have structures whose length is of the order of 1 meter, and the accelerating field in such a structure, the average field will be of the order of 60 megajoule per meter. And these are probably some of the last tests they did on a first prototype of these X-band cavities. And they actually got fields that in principle are also larger than 60 megajoule per meter. So the results were very, very good. Of course, we have the plasma module that is the heart of the EuPRAXIA Spark Lab. And on this, we did a lot of R&D, but let's say offline, we have a dedicated plasma laboratory where we test the capillaries with the plasma, and online. So we installed these capillaries in the Spark Lab test facility to test with a real electron beam. In this case, I report one of the picture we got with a 40 centimeter long capillary with EuPRAXIA. We expect a 60 centimeter long capillary. You can see the plasma that comes from a discharge, an high voltage discharge applied to nitrogen or hydrogen, depending on the gas we will use. And the gas is injected by a fast valve, in this case at 1 Hz. The opening time was a few milliseconds. And there are also several inlets to inject the gas along the entire capillary. This is the long R&D we did on the capillaries. You see, these capillaries are much shorter, are 3 centimeters, maybe 5, because at Spark Lab we don't have half GeV beam, so we have up to 100 MeV beam. And so there we tested the plasma accelerators that are shorter than the one we use in EuPRAXIA. So we did this with the first prototypes that were simply 3D printed. And then we moved to more sophisticated layouts involving different materials, because with plastic, of course, we have a lifetime that is reduced by the discharge, since we are producing a lot of heat. And so we put different materials like glass, sapphire, and what we really like now is chapal, that is a new ceramics that is has very good thermal properties and is easily machinable, so you can shape as you want, actually. And now some results, experimental results we got at Spark Lab in view of EuPRAXIA. This is a sketch of the test facility. So you see the injector is actually very similar to what will be the one in EuPRAXIA. And then we have 3 experimental beam lines. The first one hosts a free electron laser. The second one, another laser, but in the terahertz range. And the third beam line is for other tests and for user experiments. And then we have flame, that is let's say, the second pillar of Spark Lab. And actually flames will be used to drive these EUAPs, that is the EuPRAXIA Advanced Photon Source. So we will produce X-rays from Metatron radiation thanks to flame. Some of the activities are reported here. So you see an animation showing you the plasma light coming out from the capillary. In this case, it was a 3 centimeter long capillary. And also we use the plasma not only to accelerate, but for instance, to focus a beam, the so-called active plasma lens. And you can see this animation on the left. So you change the timing of the beam with respect to the plasma discharge, and you get different focalization of the beam. And also you can use the plasma as let's say manipulator for the longitudinal phase space. So if you want to change the energy spread or the energy shape of the beam, you can use a plasma to do this job. And this is what we call the chirper, because actually you can use plasma to remove the correlated energy spread on a beam. In this case, you need one single bunch. We started with this shape. You see there is a clear energy chirp, so that the tail of the beam has a larger energy. You inject into the plasma, and what you have is that you excite a plasma wake field that has an opposite slope. And so at the end, the plasma will remove the high energy content, and you exit from the plasma with a beam that has a smaller energy spread. So actually you reduce the energy spread that was at the entrance of the plasma. If we move to the plasma accelerator, instead, we have not one, but two beams at least. And these are the typical longitudinal free space we get at Spark. In this case, we have a 200 picocoulomb driver, the one on the right, followed by a 20 picocoulomb witness on the left. The energy was around 90 MeV, and the distance between the bunches is of the order of 1 picosecond or 300 micron. That is a typical plasma wavelength we use at Spark. And one of our first results with the plasma accelerator was this one we published on Nature Physics, where we actually put together the plasma accelerator and the chirper concept together. And so at the end, we obtained energy spread that was very small of the witness. You see the witness actually gained some MeV. You see the driver has a lower energy as expected. And by combining these two concepts, actually, we could achieve very small spread of the order of few, actually 100 kilo keV. And this actually was the, let's say, the main door to the FEL lasing we got then. The way this mechanism works is showed here. This is a simulation, a peak simulation. You see the witness that now enters with this in the plasma with such a chirp. Then you have the plasma wake field that has an opposite chirp, and you actually accelerate and at the same time rotate the witness phase space so that at the end, the projection, so the energy spread of the witness is smaller than the one at the entrance. That was we call the assisted beam loading technique. And with this, we actually entered into the FEL. We did this campaign in 2021. Was actually very important for us because we had to be sure that the quality of the beam was good enough to be able to lace in an FEL. That was something not trivial to do. And so what we did was to catch the witness beam after the plasma accelerator and then match into this FEL that consists of 6 undulators. The undulators were tuned in the infrared range around 80-30 nanometers. And this we got good results. We published on Nature, on PRL, and we used both the SASI scheme, so self-amplified spontaneous emission, and the seeded scheme. So the lasing was triggered by an external laser coming from Spark. And then we move on. I told you before about the plasma lens concept. So what we did was to put all together, and we built this only one device where we have the plasma accelerating module in the central part, and then 2 active plasma lenses on the side. So the beam are focused by the first lens, then accelerated in the central stage, and then catch from the second lens. And actually, we got results here. You see this energy spectrum of the beams before and after acceleration. You see a clear witness acceleration coming out of this device. So it worked. It was a proof of principle. We hope to optimize for the future. And this is also where we were installing. You see, this is actually our vacuum chamber. We have this capillary, the electro valve on the top that inject nitrogen, and then we have a screen, a scintillating screen to monitor the beam after the accelerator. And these are the high voltage discharge pulses that produce the current and the plasma, of course. And this is one of the first spectrum we got of the accelerator witness that actually gained something like 5 MeV in 3 centimeter. And last concept that probably I'm going to show you is the use of plasma to bend a beam. So we actually are doing the same as a bending magnet, but in a different way. So in this case, we have, again, an active lens that is not straight, but is curved. And so you can see here a 3D printed prototype where the channel actually is not linear, but is curved. And this is long, the length is 10 centimeter, and we have an offset of 3 millimeter between the entrance and the exit. And actually, we demonstrate here a spark that the beam was properly bent along this path. And you see from this plot, without and with the capillary turned on, the discharge turned on, your beam is deflected and then measured on the downstream screen. So this is another kind of solution using a plasma to bend the beam as alternative to classical bending magnets. And with this, I conclude. So thanks for your attention, and let me know if you have questions.
Thank you very much, Riccardo. Is there any questions from the audience? If you have a question, I think you need to raise your hand, and then I give you allow you to talk. Well, I have a question myself. So these various methods you have described for manipulating the beam to improve the quality, like the energy spread and the emittance and focusing. Are you sacrificing some of the bunch charge?
You mean for this one?
Yeah, yeah, for example.
Yeah, no, actually the charge was preserved. So that means the witness was properly injected into the plasma bubble. So the charge was preserved. We just rotated the phase space so that at the end the spread is reduced, the total spread is reduced. So that in this case was mainly correlated. And all the charge was transported along the plasma stage.
And another question, I know you're mainly interested in particle-driven plasma accelerators, but how transportable do you think are these methods for laser-driven? Can you use the same, or are they slightly different?
Actually, you can still use, because in that case, actually the laser will create the wakefield, but the slope of the wakefield will be the same. Basically, if you inject a witness with the same chip as we did here, this is still rotated and the spread reduced. So this actually should work also with a laser-driven scheme.
All right. Are there any more questions? Well, if not, then thank you very much, Riccardo, for doing this seminar. And just a reminder that the next one will be on Friday, 7th of November, at the same time. So I hope to see you all there. And with this, we can conclude.
Thanks, Riccardo.
Right. Thank you. Thank you.
Bye.
Bye-bye.